Rational expressions is basically a fancy term for simplifying fractions. It becomes a rational expression when we involve polynomials. So if we take a look at just a basic, when we look at a fraction, let's say we have something like 28 over 35. Now most of us, when we reduce this, would say to ourselves, hey, we're going to divide by 7. What does that really mean? Well, we're breaking it down into factors. We're factoring out a 7. So this is 4 times 7. This is 5 times 7. And so therefore the 7's basically factor out. We divide by them, and we end up with 4/5. This is the same principle that we're using here. Now a couple things we have to remember is that when there's multiplication involved, you can do this kind of stuff. All right? But if this was addition, all right, you just saw that. If this was addition and subtraction, it does not work just for doing that. So if I have something like 2 plus 8 over 3 plus 8, okay? Now, when I add these two together, I get 10 over 11. If I do the same thing, all right, but I just say, oh, I'm just going to cancel out these 8s, you can't do that with addition because you'll not get the same answer. When I cross out the 8s, I get 2/3. Does 2/3 equal 10/11? And the answer is no. So this is false. So you can't do this with addition. You can't cross things out. Multiplication, you can simplify. So when you have multiplication, so, and here's a simple example, 2 times 4 over 2 times, or 3 times 2. We'll go 3 times 2. When I multiply these out, I get 8/6, which simplify down to 4/3. All right, well, let's say if I started with that same problem, and I realized, you know what, I could have simplified this thing to start. I could have made that a 1, I could have made that a 2, and I go right to 4/3. That's why it works for multiplication, but it does not work for addition and subtraction. So you can simplify things, all right, and that's where factoring comes in. We're going to have to factor things. So we're going to look at a few examples here where they've already factored. So let's look at something like this where we have 5, all right, times 3 minus x, all right, all over 5x. So this has already been factored. That top equation's already had a 5 factored out. I mean, if I did distributive property, this is actually 15 minus 5x. All right. Now, the reason why I factor it to 5 times 3 minus x is now I can simplify these 5's. I can cross out those 5's, and my final answer here is 3 minus x all over x. Now again, because this is addition subtraction up above, all right, if it helps you, keep the parentheses around there. I can't cross out these 2 x's, and it's because right here it would not make it true. All right. Now let's look at another one that's already factored, all right, and see, all right, or let's look at this. Let's say I have 5x plus 3 all over x plus 3. Now in an example like this, I got to ask myself, okay, x plus 3 is as simple as it gets. It's factored. 5x plus 3 is as simple as it gets. I can't factor anything out of it. So this one is already simplified. And so sometimes that's going to happen. Now if I look at the same problem, and let's say I make it 6x plus 3 all over x plus 3. Now, up top I could try and see if anything happens. Factor out a 3 and I get 2x plus 1 all over x plus 3. But again, even in that situation, nothing else can factor out because again I have to put parentheses around here, and really so this also is as simple as it gets. Okay. Now one other example that I'm going to show you when you get a situation like this is going to happen to you where you get 5 minus x over x minus 5. They look very similar, but they certainly aren't going to cancel each other out. But here's what they do equal. Take the one that's not in standard form and factor out a -1, and then I get x minus 5 all over x minus 5. So now I've created 2 binomials that are the same by factoring out the -1. I can get back to my 5 minus x when I multiply by a -1. Now my x minus 5 cancels, so this equals -1. So anytime you see this situation where you have the really 5 minus x, kind of the opposites of each other, all right, and that's what they are. Each one's the opposite. That equals a -1. All right, so let's take a look when you have to actually factor one of these. So let's look at this example. We got 15x, all right, over 5 minus 10x. Now anytime I have a binomial, I'm going to look for two things. I'm going to look for the difference of squares, and I'm going to see if I can factor out the greatest common factor. So anytime I get a binomial, that's what I'm going to look for. So first of all, 5 minus 10x is not the difference of squares, because 5 isn't a perfect square, 10 is not a perfect square. But I can factor out a greatest common factor. So what I'm going to do here is I leave the 15x alone. Monomials, there's not much you can do with monomials. You just leave them and see if something else can factor into them and reduce them. So now I factor out a 5, and I get 1 minus 2x. Now I can do something with the 15 and the 5. The 5 becomes a 1. This 15 becomes a 3. So my final answer is going to be 3x all over 1 minus 2x. Now I need to check to find out when something is undefined. Okay? A fraction is undefined when the denominator is 0. So I have to check for undefined, which basically means I have to check to see if the denominator, all right, the denominator is 0, or when it's equal to 0. So I take my denominator, my 1 minus 2x, and I set it equal to 0. In this case, I'm going to get 1 equal to 2x. When I divide by 2, x is equal to 1/2. So basically what we're saying, for this fraction, or this rational expression, x cannot be a half. If x is a half, then it is undefined. All right. Let's look at one more example, and then we'll look at a word problem. All right, so when we take this example here, we got x squared, all right, plus 6x plus 9 all over 9 minus x squared. All right, so again, what we're going to do here, I'm going to take my eraser here, and I'm going to erase this check that I did over here. Let me get the bigger one. That's not the bigger one, but we'll erase this and give us a little bit more room here. There we go. Okay, so first thing I got to do, again, I have a trinomial and I have a binomial. What you're going to do is you're going to look to factor. So I have this binomial. I said look for difference of squares, greatest common factor. 9 minus 10, or 9 minus x squared is the difference of two squares. So this is going to be 3 plus x times 3 minus x. All right, all over, now this is a trinomial, so again I'm going to look to factor into two binomials. And because I got plus plus, and if I actually recognize this is actually one of those other special products, it's a perfect square trinomial, so I'm going to get a 3 and 3. And again, I can get back to my 6x, my inner and outside. It's 3x plus 3x. Now, the obvious one by commutative property, these are the same. X plus 3, 3 plus x is the same. Now, when I look here, I have to look, okay, is this the same? And well, again, the answer is no, because we have plus. So there's no way I can make this to be the same. So my final answer is x plus 3 all over 3 minus x. Now, when is it undefined? It would be undefined when my denominator is 0. So when x becomes 3, it is undefined. Right? So that's what I have to do when I have rational expressions. So when I have binomials, I look for the difference of two squares. I look to factor out greatest common factors. When I have trinomials, all right, so when I have trinomials, what I look for, one is I look to factor, all right, into two binomials. The other thing I can look for is still look for the greatest common factor. All right, and then once I factor that out, then I look to maybe factor into two binomials. So a lot of different things that you can look for.